In this presentation, we have talked about the laws of thermodynamics. First case is zeroth law of thermodynamics. Consider three systems A, B and C. Suppose the systems A and B are in thermal equilibrium with the system C, then they are in thermal equilibrium with each other. This means that all the three are at the same temperature. Read out this statement. If two bodies A and B are in thermal equilibrium with a third body C, they must also be in thermal equilibrium with each other. This means that all the bodies are at the same temperature. F suffix A, P of A, V of A equal to F suffix B, P of B, V of B equal to F suffix C, P of C, V of C equal to T. These equations are known as equations of the state of a system. Temperature is a thermal condition of a substance and measures its relative hotness. The consequence of zeroth law of thermodynamics is temperature. Now we will go to the first law of thermodynamics. The quantity of heat energy given to the system is equal to the summation of change in internal energy of the system and the external work done by the system. Consider a working substance. This is a friction-free piston. Inside the working substance, a perfect gas is present. Suppose work is done by the working substance. The piston is moved to some extent in the upward direction. Now this is change in length delta L. Now the work done is equal to force into distance moved. But force acting per unit area is called pressure. Therefore, F is equal to P into A. Now, del W, which is equal to pressure into area, then the distance moved is delta L. Delta L. This A into delta L is dV, change in volume. So, P dV. In this way, we have replaced this delta W by P dV. Here, for the quantity of heat energy and work done, we have given inexact differentiation delta. For internal energy, we have given exact differentiation D, because the quantity of heat energy and work done are path functions, whereas the internal energy is the state function. Read out this. Here du depends on the initial and final state of the system. The terms heat and work depend not only on the system's initial and final state, but also on the path along which the state transformation has taken place. The consequence of first law of thermodynamics is internal energy. The major drawback of the first law is it doesn't say anything about the direction of heat flow. Now we will go to second law of thermodynamics. It has two statements. One is Clausius statement and another one is Kelvin statement. In the case of Clausius statement, it is impossible for a self-acting machine unaided by any external agency to transform heat from a cold body to a hot body. Without the help of an external agency, it is not possible for us to transform heat energy from a body at a lower temperature to a body at a higher temperature. This is Clausius statement. Now, the Kelvin statement is, it is impossible to get continuous heat energy from a body by cooling it to a temperature lower than its surroundings. You may get heat energy from a body to certain extent. If you want to get heat energy from a body by cooling it to a temperature lower than that of its environment, it is highly impossible. This is Kelvin statement. Now we may go to third law of thermodynamics. The entropy of a substance tends to be zero at absolute zero temperature. You know the concept entropy. The quantity of heat energy either given to the system or taken away from the system divided by temperature of the system is called change in entropy, ds. The entropy approaches zero at absolute zero temperature. Absolute zero means 0 Kelvin or minus 273.16 degrees Celsius. This is called absolute zero. These are all called laws of thermodynamics.